Resume. Okay, so welcome everybody. Today's speaker is Daniel Egana-Ugrinovic. He will discuss about sources of low energy events in dark matter detectors, so a very important talk for these days. So Daniel got his PhD at Rutgers University, and then he moved towards postdoctoral position at Stony Brook University, and currently is at Perimeter Institute for Theoretical Physics. And he got the Simons Fellows at the Perimeter Institute for Theoretical Physics. So I'm going to leave you discuss the sources of low energy events in dark matter detector. Thank you very much, Daniel, for being here. Thanks.
Thanks, Silvia, for the invitation and for the nice introduction. It's a pleasure to be here with you remotely. Hopefully in the future I will be able to go physically. You are not that far.
Yes, indeed. You have an invitation.
So today I want to tell you about work that we have been doing in collaboration with Pei Sidhu, Ruben Essig, and Mukul Sholapurkar. And the objective of today's talk is to tell you about a series of novel and previously unexplored backgrounds which very significantly affect light dark matter detectors, and they affect their reach to actually discover dark matter. Moreover, I will show you evidence in favor of the interpretation that some of these experiments are already seeing a large number of anomalous events at low energies, and I will try to convince you that the backgrounds that we will discuss today are indeed a very likely explanation for those excess events that are seen at some of these experiments, in particular SENSEI and SuperCDMS HVeV. Now, as you know very well, there's a tremendous variety of detectors trying to discover dark matter. Now, since we don't know what's the mass of the dark matter particles, the detectors collectively try to cover as much mass range as possible, ranging from fractions of an electron volt to hundreds of TeV and even beyond. Now, for the purposes of this talk, I will concentrate on detectors looking for dark matter in a very specific mass range, roughly between the electron volt and 1 GeV. Okay, so the models of dark matter that fall within this mass range go under the name of light dark matter theories. And in fact, there's a wide variety of very well motivated theories that in which dark matter could precisely have these sub-GeV masses. Now, one of the possible ways in which you could try to discover these dark matter particles is by building an experiment that looks for the scattering of dark matter out of a detector target, and therefore deposits energy in the detector target. And as an experimentalist, one of the first things that you would like to know regarding such a scheme is how large are the typical energy depositions that you expect from such a scattering event. Now, those energy depositions are very simple to estimate. The maximum amount of energy that the dark matter can leave in your detector by scattering is just its full kinetic energy. And plugging in some numbers, so knowing that the velocity of dark matter locally is around 200 kilometers per second, and plugging in a dark matter mass of roughly 1 mega electron volt, which is within the range of masses that we're interested, you get that the typical energy depositions that you can expect from light dark matter are of the order of 1 electron. Now, these energy depositions are very, very small. However, they are sufficient to create electronic excitations in materials. In fact, if you think about differences of energy levels of electrons in a material, for instance, the difference of energy levels in the hydrogen atom of different electrons, then you will immediately remember that those differences are of the order of electron volt. Therefore, most of these light dark matter experiments are trying to detect electronic excitations created by dark matter. Now, one possibility is that these electronic excitations are the creation of electron-hole pairs. So the idea in this scenario is that dark matter scatters out of a semiconductor target. And in doing so, it excites an electron from the valence band of your semiconductor into the conduction band, creating an electron-hole pair. If you can read out that electron-hole pair, then you can gain access into the dark sector. Now, these excitations are indeed created by dark matter. However, the energy depositions that we're talking about are still very small, and traditionally they were out of reach from experiments. But in the past few years, there have been important experimental developments which have precisely allowed you to reach the low energy thresholds required for detection of light dark matter. That progress is illustrated in these two panels here. Here I'm showing you the energy resolution of one type of detectors that tries to detect the creation of electron hole pairs, which are charge-coupled devices. On the left panel, I'm showing you the energy resolution of a traditional charge-coupled device, and on the right panel, the energy resolution of a new improved charge-coupled device. So if we start with the panel on the left, you see that the energy resolution of traditional charge-coupled devices was of the order of 10 electron hole pairs. That means that you needed to create 10 electron holes per event in order for you to be able to detect that event. 10 electron hole pairs, the creation of 10 electron hole pairs requires approximately 10 electron volts in typical semiconductor targets such as silicon. And those energies are larger than what light dark matter will deposit generally in your detector. Therefore, these detectors here, traditional CCDs, were not able to detect light dark matter. However, on the right panel now, I'm showing you the energy resolution of a new type of CCD, which goes under the name of skipper CCDs, which has a significantly improved energy resolution. And from this panel here, you immediately see that the energy resolutions are now sub-electron. That means sub-electron volt. The state of the art now is that then energy depositions as low as 1 electron volt are detectable in detector setups with targets as large as 10 grams. Okay, so that now allows you to try to discover light dark matter. Now, the combination of these important experimental developments and very strong theoretical motivations have led to an explosion of experiments looking for light dark matter. And this plot here is an illustration of that. This plot is an exclusion plot on one particular type of light dark matter models, which is a dark matter particle which scatters out of electrons via a light mediator, which is called a dark photon. And these exclusion plots are shown as a function of the dark matter mass. So we're looking for sub-GeV masses. And you see that there's a significant amount of experiments looking for light dark matter. There's SENSEI, Edelweiss, DAMIC, SuperCDMS, and many others. Currently, the best limits are set by SENSEI, but many other experiments are trying to compete. And importantly, most of these curves are actually from experiments that have taken data in the past few years. So most of this data is kind of new. Moreover, in the following years, there have been like a significant amount of proposals to try to improve these bounds. And in fact, many theorists and experimentalists are thinking on how to push these bounds towards lower cross sections and lower masses. And there are different ideas on how to do that. So this is clearly a very lively topic of research right now. Now, very interestingly, most of these light dark matter experiments, which have already taken data, are seeing a large number of excess events at low energies. Okay? And this is even after applying all their analysis cuts in order to discriminate potential dark matter signal events from known backgrounds. Now, these excess events are seen by a variety of experiments, but for concreteness, I'm going to concentrate in this talk mostly on two specific experiments, SENSEI and SuperCDMS HVeV, which have very different technologies, so we will take as representative of a broader class of experiments looking for light dark matter. These two panels here are showing you a representation of the excess events seen by SENSEI and SuperCDMS HVeV. So let's start with the events seen by SENSEI. So on the left panel, the blue dots show you the rate of single electron events seen by the SENSEI experiment as a function of a parameter of their analysis, which is called the halo radius. For now, it's not important what's the halo radius. What I want you to see from this plot is that the rate of events that they are seeing, regardless of the halo radius parameter, is non-zero. And again, this is after applying all their analysis cuts to discriminate dark matter events from known backgrounds. Okay? They do not know what is the origin of the single electron events, at least up to the time of publication of their latest results from 2020. On the right panel, you're seeing a similar plot by the SuperCDMS HVeV experiment, which uses a very different technology than SENSEI. SuperCDMS HVeV is an experiment that has excellent timing resolution. Therefore, they classify events in n electron beams with n going from 1 to 6. And the events are classified regarding on how many electron hole pairs are created per very short time window, in a time window of roughly 100 microseconds. So if you create one electron hole within 100 microseconds, that's the first electron hole beam, 2 electron holes in the same window, 2 electron beam, etc. All these peaks that you show here are precisely the electronic beams that they separate their data in. And the solid line is what they are actually measuring. And you see that this solid line, regardless of the n electron beam that they are trying to measure, it's non-zero. And this is even after accounting for all their known backgrounds. Okay? And imposing analysis cuts to try to get rid of those backgrounds. And again, they do not know what's the origin of these backgrounds, at least they didn't at the moment of publication of their results. Now, both theorists will tell you that perhaps these events that we're seeing at low energies are the first manifestation of the discovery of dark matter. After all, these events do look like dark matter. However, much more conservatively, I will try to demonstrate to you that most likely these events are not dark matter, but instead they are low energy photons which arise from tracks that pass through detector materials. And these low energy photons will be created via two very specific processes. One is Cherenkov radiation and the other one is radiative recombination, also called luminescence. So the big picture idea will be the following. The big picture idea is that a typical light dark matter detector looks as follows. You have a detector, which is a semiconductor target, can be silicon, germanium, which is usually held by some auxiliary materials, which are usually dielectrics, Teflon, plastic, things like that. Around this setup, you usually have some metallic housing that is usually also copper. Okay? So the idea is the following. The idea is that tracks, electrons coming from radioactivity or muons from a cosmogenic origin will pass through your detector target, through your semiconductor, and as they pass through the semiconductor, they will create low energy photons via the Cherenkov process or radiative recombination. These low energy photons then will travel and will get absorbed in your semiconductor target by scattering out of an electron of the valence band and exciting it into the conduction band, creating in this way an electron-hole pair. Since dark matter events are also classified as events that create electron-hole pairs, then these low energy photons do indeed mimic dark matter events and they constitute backgrounds. An alternative is that tracks can pass through auxiliary materials, which are not instrumented, such as the plastic holders of your detector or any plastic circuit boards, cables, etc., creating low energy photons in those materials, which then travel, can scatter out of the walls of your metallic housing, which is essentially a mirror, until they are eventually absorbed in your detector, constituting in this way backgrounds. Okay. So we have lots of things to do in order to understand these backgrounds in more detail. So we're going to separate this talk in many parts. So first of all, I'm going to give you some theory basics. I'm going to remind you what's the Cherenkov process, how low energy photons are created via the Cherenkov effect, and then I'm going to remind you what's radiative recombination, which is also called luminescence or scintillation. After that, we will analyze these low energy backgrounds at SENSEI and SuperCDMS HVeV, and I'm going to try to convince you that these low energy photons can indeed explain the excess events seen by both SENSEI and SuperCDMS. After that, we will look towards the future and we will see how these backgrounds can affect future experiments, in particular SuperCDMS at SNOWLAB. And I'm going to try to show you that these events will or potentially will dominate the background seen by SuperCDMS SNOWLAB at low energies. And finally, we will discuss very concrete mitigation strategies in order to get rid of these backgrounds towards the future and significantly improve the reach of dark matter detectors to discover dark matter particles. Okay, so let's start with Cherenkov radiation. So Cherenkov radiation is the spontaneous emission of radiation by tracks that pass through dielectric non-conduction materials. So the diagram is just here. It's an electron or a muon that passes through your dielectric material, spits out a photon spontaneously. Now, this process does not happen in vacuum. In vacuum, this process is not kinematically allowed, but it can happen in materials. Therefore, the materials need to satisfy a condition in order for this process to happen. And that condition is written here. The condition is that the velocity squared of your particle times the dielectric function of your material, which is a frequency-dependent quantity, it depends on the frequency of the photon, must be larger than 1. This condition is nothing else than requiring supraluminality in the material by the track. Okay? Now, from this condition, you immediately see that Cherenkov radiation doesn't happen in vacuum. In vacuum, the dielectric function is 1, so that will tell you that the velocity of your particles should be larger than 1. Particles in vacuum do not travel faster than the speed of light, therefore that cannot happen. Okay. Now, Cherenkov radiation has very specific characteristics. First of all, the photons are emitted in a very specific angle, which is called Cherenkov angle, which you can calculate from the velocity of your track and the dielectric function of your material. And secondly, the rate of Cherenkov photons emitted per unit frequency of the photon per distance x traveled by the track has a very simple expression. It's just proportional to 1 power of the fine structure constant, and it has a correction that depends on the velocity of the particle and the dielectric function of your material. Now, why should you care about Cherenkov radiation as a source of low energy backgrounds? There are 2 reasons for that. The first one is that Cherenkov photons naturally have ordered electron volt energies, which is precisely the typical energy depositions that you would expect from light dark matter in a semiconductor target. That we can see from the Cherenkov condition very directly. So the Cherenkov condition tells you that the velocity square of track times the electric function needs to be larger than 1. Therefore, a necessary condition for this to happen, since velocities are always smaller than 1, is that the dielectric function must be larger than 1. Okay? And we can see when it's that realized in typical materials. So consider, for instance, silicon and germanium, which are typical detector materials. Here I'm plotting the dielectric function for silicon and germanium as a function of the photon frequency. And you see that the dielectric function of these two materials is larger than 1 for frequencies roughly less than 4 electron volts. Therefore, Cherenkov radiation in these materials is supported only up to energies of 4 electron volts. All Cherenkov photons have energies below 4 electron volts. Therefore, you see clearly that Cherenkov radiation has precisely ordered electron volt energies, which is what you will expect from a dark matter event. The second reason why you should care about Cherenkov radiation is that the rate for Cherenkov emission is big. And the reason is that the Cherenkov process arises at leading order in electrodynamics. It's spontaneous emission of light. Therefore, it's proportional to only 1 power of the fine structure constant. Therefore, the rate is big. We can estimate how many Cherenkov photons are emitted per track just to get an idea. And in order to do so, consider, for instance, an electronic track of 100 keVs, which roughly travels of the order of 100 micrometers in silicon before being stopped. Okay, and let's calculate how many Cherenkov photons do we get out of that. Let's concentrate on Cherenkov photons with energies within, say, 1 to 2 electron volts, so an energy span of 1 electron volt. And the answer is that you get 4 Cherenkov photons per track, approximately. Usually, in experiments such as SENSEI and SuperCDMS HVeV, you get hundreds, if not thousands, of tracks per gram-day exposure. Therefore, you can get thousands of Cherenkov photons easily within your detector exposure, which then can mimic dark matter. Now, in order to put things in context, let's compare Cherenkov radiation with another very well-known radiative process, which is bremsstrahlung. Now, bremsstrahlung happens when a track, an electron or a muon, scatters out of the nucleus of your target, and after doing that, it emits a photon. This process is not spontaneous emission of light. You first need to scatter out of the nucleus. As a consequence, this process has 3 insertions of the fine structure constant, one here, and one here. It arises at third order in electrodynamics. Therefore, this process is naturally suppressed with respect to Cherenkov radiation, and therefore the rate of emission of low energy photons by bremsstrahlung, you can actually check that it's usually a couple of orders of magnitude below the Cherenkov process. Therefore, Cherenkov radiation is the main source of the emission of low energy photons directly from the track. However, there are other processes by which tracks can emit light indirectly, which are even more efficient than Cherenkov radiation. And that takes us to our next process, which is radiative recombination, which is also called luminescence, also called scintillation. Okay, so the idea here is the following. So radiative recombination is the emission of photons as excited electrons in a material return to their ground state. So the idea here is that a track will pass by through your semiconductor target or any material around the semiconductor target, exciting several electron hole pairs. Now, these electron hole pairs, they will like to recombine because it's energetically favorable. At some point, they will like to recombine. And one possible way by which they can recombine is by emitting low energy photons. Okay. And these low energy photons then can travel in your detector and be absorbed somewhere and constitute a background. Now, why should you care about radiative recombination? There are 2 reasons again. First of all, the photons that you get out of radiative recombination naturally have energies of order of electron volt. And that's by definition. And the reason is that the typical energy differences between the valence band of a semiconductor and the conduction band are precisely of the order of an electron volt. Therefore, the photons that you will get out of this recombination process are of the order of an electron volt, which is again what you will call a signal. A dark matter event deposits roughly an electron volt in your detector. That's the first reason. The second reason why you should care about radiative recombination is that the rate of emission can be gigantic. And the reason is that tracks do not leave most of their energy in the material by emitting Cherenkovs or bremsstrahlung or nothing like that. Instead, what they do is that they leave most of their energy in a material by creating a gigantic cloud of electron hole pairs. To give you a sense of numbers, a single 200 keV electron track, which travels 200 micrometers in silicon before being stopped, creates 60,000 electron hole pairs before being stopped. if all these electron hole pairs were to recombine radiatively, you will get a gigantic soup of low energy photons flying around your detector, which could constitute backgrounds. However, fortunately, not all electron hole pairs in materials recombine radiatively. And the reason is that there are competing processes for this recombination to happen. And the amount of photons that you get out of radiative recombination, it's a very material dependent question. So in order to see what are the main competing processes, you need to know which material are you talking about. So let's consider two specific examples. Let's consider the example of a track traveling through undoped silicon and then doped silicon. And let's try to calculate how many radiative recombination photons do we get out of the track. Okay. So let's start with the case of undoped silicon. Now, without proof, I'm going to tell you that the main competing process to radiative recombination, which suppresses the radiative recombination rate, is the diffusion of electron hole pairs. The idea here is the following. The idea is that you create a whole cloud of electron hole pairs and they want to recombine by emitting photons, but diffusion takes the electron away from the hole. So the electron and the hole cannot find each other anymore to recombine. Therefore, diffusion suppresses the radiative recombination rate. So how can we get then an estimate on how many photons do we get per track passing through our undoped silicon example? Okay. So we take our 60,000 electron hole pairs that we start with from the single 200 keV track, and we multiply with the branching fraction to recombine radiatively, which is nothing else than the competition between diffusion and radiative recombination. So you just take the fraction of the diffusion time or the radiative recombination time. So I did this calculation for you, and the number of photons that you get out of the 60,000 electron hole pairs, it's only 10 to the minus 5. It's a tiny number. Therefore, in materials such as undoped silicon, radiative recombination is not a source of low energy photons, it's not a source of concern. The situation is dramatically different though in other materials, such as doped silicon. So consider doped silicon with a doping concentration of 10 to the 18 dopants per centimeter cube. Okay. Now, without proof, I'm going to tell you here that the main competing process to radiative recombination is not diffusion. It's another process, which is the recombination via phonons, via emitting phonons, okay? And just in the interest of time, again, I'm not going to show that for you, but you can, this is a more or less well-known fact. Anyways, so how do we calculate the amount of low energy photons that we get out of our track then? We take our 60,000 electron hole pairs, we multiply with the branching fraction to recombine radiatively, which is now the fraction between the phonon recombination time and the radiative recombination time, and you get a number that is 600. So you get 600 photons per track. It may seem like a small number because you started with 60,000 electron hole pairs. However, it's huge. If you compare with the number of Cherenkov photons that we were getting out of our single electronic track a few slides ago, we were getting 4 photons per track. Here we're getting 600. So when a track passes through a material such as doped silicon, it emits several low energy photons, which then can mimic your dark matter signal. The comparison between these two numbers, the number of photons that you get in undoped silicon or in doped silicon, is nothing else than a manifestation of the fact that doped silicon is a good scintillator. It emits lots of photons when tracks pass through doped silicon, and undoped silicon is not a good scintillator, so no photons come out of that. Okay. Therefore, this immediately tells you that if your material is a good scintillator, such as doped silicon, gallium arsenide, etc., when your track passes through the material, it would emit several low energy photons that then can constitute backgrounds. Great, so now we have the main theory tools to try to estimate the backgrounds that arise at several experiments. So let's start with SENSEI. Okay. So SENSEI is an experiment that took data in 2020, and it had an effective exposure of 1 gram daily. The way that SENSEI works is that it uses a CCD, a specific type of CCD, a skipper CCD, which we already encountered, to detect the creation of electron hole pairs as dark matter scatters out of a silicon target. The target is the CCD itself, which is made out of silicon. SENSEI was located 100 meters underground at the Minos cavern, inside a copper vessel, surrounded by further lead shielding to shield it from tracks that will pass through your detector. Okay. Now, even though SENSEI was pretty well shielded, they still saw a large number of tracks passing through their detector. So this is an actual image from the SENSEI CCD. The CCD is nothing else than a piece of silicon separated into very small pixels. for our purposes. So in this image that it's a measurement for SENSEI, you see these long tracks here. These long tracks are nothing else than muons. You see short curly tracks, those are electrons, and you see bright dots, which are X-rays. Now these big energy depositions, muons, electrons, or X-rays, they are clearly not dark matter. Dark matter-like events look differently. The dark matter-like events are these tiny dots that you see here in the background, okay? Therefore, SENSEI has to discriminate in some way these big energy depositions from the tiny dots that are dark matter-like events. They need to impose vetoes in order then to discriminate these tracks from dark matter-like events. Now, SENSEI does not have good timing resolution. The time resolution of the detector at SENSEI is of the order of hours. Therefore, it's not that they can see a track and veto it immediately and keep taking data. That's not possible at SENSEI. Instead, what they do in order to suppress track backgrounds, which are clearly not dark matter, these things are not dark matter, they use their excellent position resolution. The idea is the following. The idea is that they see this track and they say, look, this thing is clearly not a dark matter event, so we need to veto it. So they veto all the pixels over which this track went by, and moreover, just to be sure, they veto a whole cylinder of pixels around the track. They just remove all those pixels from their analysis. The radius of the cylinder that they draw around the track and that they veto is called the halo radius. Okay, and that's the parameter that we were seeing in the first few slides. With the standard analysis, they veto 60 pixels away from any track, and they drop all those pixels within that cylinder. So that's their main analysis cut to discriminate dark matter signals from actual backgrounds, which are tracks or things like that. Okay, but they have other cuts too. Now, even after imposing this cut and many other cuts, they still see a large rate of electronic excitations in their CCD, a large rate of creation of electron hole pairs. The rate that they see with their standard halo radius, which is 60 pixels, is 450 events per gram day. And at the moment of publication, they did not know what's the origin of these events. Okay? But they knew two things. They knew first that the rate depended on the amount of background radiation. It depended on the amount of tracks that were passing through the CCD. And that they knew because they took data with two different configurations, one with high shielding, leading to a low number of tracks passing through the CCD, and another one with low shielding, leading to more tracks passing through the CCD. And they saw that the more the tracks that they pass through the CCD, the larger the one electron rate that they observed in their CCD. So clearly this background was related with tracks. An additional piece of evidence in favor of telling you that these backgrounds were coming from tracks is the following. Their standard analysis uses a halo radius cut of 60 pixels, this one here. And 60 pixels correspond to 450 events per gram day. However, they modified that parameter in their analysis in order to see how the rate of single electron events depends on the radius of the cylinder that they draw around tracks that vetoes all those pixels. Okay. And they saw that the larger the radius that they took, that means the more the pixels they drop away from tracks, the smaller the rate of electronic excitations that they see. And the smaller the radius that they took, that means the closer that they look to tracks, the larger the rate of single electron events that they saw. So again, this background was clearly related with tracks. So now I'm going to show you how those backgrounds arise due to these two processes that we just discussed. So in order to do that, let's take a look at a schematic view of SENSEI. So SENSEI looks as follows. SENSEI uses a skipper CCD, which is made of silicon, which is their actual detector. And on top of the skipper, they have another chunk of silicon, which is the pitch adapter, which is just a piece of silicon that is there to hold the CCD. And then there's copper around it, okay, some copper vessel. So let's see how backgrounds arise in this configuration. Let's start with Cherenkov. So the idea here is the following. The idea is that a track, an electron or a muon, will pass through the pitch adapter and the CCD. And since these two materials are silicon, they are dielectrics, then this track emits Cherenkov light. Okay? So as the tracks pass through these two pieces of silicon. These Cherenkov photons then travel around your CCD. They may scatter out of the surfaces of the CCD or out of the surfaces of the copper until they are eventually absorbed somewhere. The two main pieces of absorbing material within their copper housing are the pitch adapter and the CCD. They are roughly the same size. So roughly half the Cherenkov photons get absorbed in the CCD and constitute a background, and the other half get absorbed in the pitch. So that's one of the sources of backgrounds at SENSEI. The second source of backgrounds is radiative recombination. And here the story, it's a bit different. So the idea here is that tracks pass through the CCD, which is made out of high purity silicon. Now, I told you that in undoped high purity silicon, tracks that pass through the CCD, they create this whole cloud of electron hole pairs, but they do not recombine radiatively efficiently. Okay, so I demonstrated for you that the branching fraction for electrons and holes to recombine radiatively in high purity undoped silicon is very, very low. Undoped silicon is not a good scintillator. However, you must be careful. And the reason is that if you zoom into the backside of the CCD used by SENSEI, and actually any CCD, you will see that in the backside of the CCD, there's a large amount of foreign materials in addition to silicon. In particular, in the backside of the SENSEI CCD, there are layers of very highly doped silicon, doped with phosphorus. So this plot here is showing you the phosphorus concentration, which is a dopant, as a function of the distance from the backside of the CCD. And you see that the phosphorus concentration reaches values as high as 10 to the 20 per centimeter cube. So it's a huge doping concentration. And this doped layer of phosphorus, it's very thin. It's roughly 5 micrometers. It's tiny. It's a tiny layer. However, I showed you that in doped materials, the radiative recombination rates are extremely large. Tracks that pass through doped materials emit light very efficiently via radiative recombination. Those materials are very good scintillators. Therefore, we must take that backside into account in order to calculate backgrounds. So then the idea is that the track will pass, it will pass through the backside of the CCD, and it will emit some photons that then will get absorbed in the CCD, constituting a background. Okay. So how do you do the calculation of the backgrounds? You do a simulation. So we did a simulation of tracks passing through the CCD at SENSEI and emitting Cherenkov photons and radiative recombination photons. So this is a picture of our simulation of the CCD. So these long tracks are again muons, shorter ones are electrons, the dots are X-rays. And this picture here is the same figure, but now I have overlaid the Cherenkov photons in like this orangey color, brownish color, and the radiative recombination photons in black. And the points show where those photons were absorbed, not where they were emitted. The points show where they are absorbed, okay? So let's start by inspecting the Cherenkov photons. So from this picture, you clearly see that most Cherenkov photons, they are emitted from tracks and they are absorbed very close to the underlying tracks. And the reason is the following. That we can see from just from plotting the mean free path of a photon in silicon as a function of the photon frequency. And that's done here. You see that the mean free path of a photon, of a Cherenkov photon in any photon, for energies roughly larger than 1.5 electron volts, is less than 1 pixel. That means that the photon gets emitted from the track, and within 1 pixel, it gets immediately reabsorbed. Those photons are not a source of background SENSEI. And the reason is that I told you that there's this cut, that they cut this whole cylinder of pixels around tracks to get rid precisely of these backgrounds. So those photons are not a background. However, some Cherenkov photons have energies which are lower. And in particular, some Cherenkov photons have energies that are very close to the silicon bandgap. And for those energies, the mean free path of photons in silicon gets extremely large. The reason is that then it becomes phase space suppressed for the photon to be absorbed into an electron hole pair in silicon. Therefore, those Cherenkov photons with near bandgap energies can travel far away from tracks, avoid this halo mask cut, and constitute in this way backgrounds. And that we actually see from our simulation. So you see that there are some Cherenkovs like this one here, which is not associated with any track. Okay, so those guys are indeed backgrounds. Now, radiative recombination photons, on the other hand, they are by definition near bandgap. They arise from the recombination of an electron hole pair across the bandgap. So they have near bandgap energies by definition. Therefore, they always travel away from tracks, and most of them, they constitute backgrounds. And then you see again from our simulation here, these black dots, they are clearly not really related with any underlying track. They just travel away from their underlying track, and then they get just homogeneously distributed in this CCD. Okay. So now we can calculate how many backgrounds do we get from these two processes, and the answer is the following. So with our latest simulation, the rate of Cherenkov photons that we get from this track that pass all analysis cuts that they are actual backgrounds, it's 130 per gram day. And the rate of radiative recombination photons that you get is between 110 to 770, where this large difference is due to large systematics in the calculation of the radiative recombination backgrounds, which we're actually working on. Okay? So if you sum these two numbers, our interpretation of the backgrounds tells you that you should see from anywhere between 240 to 900 events per gram day at SENSEI. And this needs to be compared with what they actually observed in data, which was 450. So from this comparison, you see immediately two things. First of all, our interpretation is in the right ballpark, right order of magnitude. So that's already pretty strong evidence in favor of these two background processes constituting a large chunk of the backgrounds observed by SENSEI. But the second thing that you see is that our systematics are large. And the reason is that the calculation of the radiative recombination backgrounds depend very precisely on the materials found in the backside of the CCD. So we need to know what those materials are very precisely, and we need to simulate the backside of the CCD to utmost detail. And we're actually working on that, so this systematic will get down significantly after we improve our simulations. However, even though these numbers are in the right ballpark, we have even additional evidence in favor of these two processes constituting the backgrounds that SENSEI is observing. And the evidence comes from the following. So I told you that SENSEI took data for different halo mask radii. So this line here is the data, and we saw that the rate of single electron events that they observed was smaller the larger the halo mask radius that they took, okay? And the closer they observed to the track, the smaller the halo mask radius, the larger the rate of events that they see. This is our simulation, okay? With the lower end of the estimate, 240, this is our simulation. So it clearly has the right shape, okay? So with this, we take as further pretty strong evidence in favor of our interpretation of the background events that SENSEI is observing. So let's move to the next experiment. Let's move to SuperCDMS HVeV, which took data in 2019 with an effective exposure of roughly a gram day. So SuperCDMS HVeV uses a completely different technology than SENSEI. The idea here is the following. SuperCDMS HVeV has a silicon target, which is here. This is an actual picture of the experiment, which is here, which is in an electric field. The idea here is that dark matter comes, scatters out of an electron, creates an electron hole pair, and the electron hole pair is drifted up and down by this electric field. As these electron holes are drifted, they create several phonons via an amplification process that's called the Egana-Ugrinovic effect. Then SuperCDMS HVeV reads out those phonons. Okay, so that's the way that they detect the creation of these electron hole pairs. Now, SuperCDMS HVeV was located at surface, so it was exposed to a large number of tracks at Northwestern University. Okay. Now, the results were the following. So as I already told you, SuperCDMS HVeV had excellent timing resolution, differently from SENSEI. So they classify events, electronic events, with from 1 electron events to 6 electron events, depending on how many electron hole pairs were created per timing window. And their timing window was very, very short. It's 100 microseconds. So they have very good timing resolution. And regardless of the electronic beam that they observed, how many electron hole pairs were created per timing window, they see a large number of events. So for the 1 electron beam, they see roughly 100,000 events, 2 electron beam, 1,000 events per gram day, etc. So they have a large number of events. Now, the rate for 1 electron events, they roughly understood. They believe that is due to charge leakage. They are electron hole pairs which are created in impurities of their bulk detector, somehow make it into the TS, in some way deposit energy there, and create backgrounds. But the 2 to 6, they don't understand at all. They did not have, at the moment of publication, an hypothesis for the origin of the events in the 2 to 6 electron beam. So that's what we're going to do. We're going to try to explain the 2 to 6 electron beam using these low energy photons that we have been talking about. Okay, so the idea is the following. So let's start with a schematic view of SuperCDMS HVeV. So the detector looks as follows. You have a silicon target. It's clamped between 2 plastic circuit boards, which are uninstrumented. These 2 ones here. There are some further plastic connectors around, and everything is surrounded by some copper vessel. Okay. So how are backgrounds going to arise? First of all, to our knowledge, there's no scintillating material that can lead to radiative recombination photons within their detector. Therefore, we're just going to drop, to be conservative, any radiative recombination potential backgrounds, and we're only going to concentrate on Cherenkov photons. Okay. The idea will be the following. The idea first is that any track that passes through the silicon target here in this color will create low energy Cherenkov photons that can constitute backgrounds, but remember that SuperCDMS HVeV has excellent timing resolution. Therefore, any track that passes through their actual detector will get immediately vetoed. That's not a background. They veto it out, it's not a source of concern. However, tracks can pass through uninstrumented materials, such as the plastic circuit boards, and they can create Cherenkov photons there. And those Cherenkov photons will not be vetoed, so they will constitute backgrounds. So how do you calculate those backgrounds? Oh, sorry. And well, these Cherenkov photons first, they just will travel around your PCB, they will escape the PCB, they will bounce in your copper walls, and then eventually they can be absorbed in the detector. Okay, so how do we calculate those backgrounds? It's actually not that hard. So we're going to do the estimate as follows. In order to calculate how many Cherenkov backgrounds you get from tracks, first of all, you need to know the number of tracks. Okay, so that's not published by SuperCDMS HVeV. So we're going to take the rate of tracks seen by an experiment which had a similar surface exposure, which is SuperCDMS HVeV. And then we're going to assume that the spectrum of the tracks is the same as SENSEI. So the idea is that tracks will pass through this PCB, and some of them will pass through the center of the PCB and create Cherenkov photons, but those will get reabsorbed in the PCB before escaping and making it into the detector. So we will only consider tracks that pass through the borders of the PCB, more specifically within 1 mean-free path of the photon from the borders of the PCB. And using those tracks, we can calculate the total number of Cherenkov photons that just are produced by these tracks and escape the PCB. That's not hard, okay? The hard part of the calculation is that once the photon escapes the PCB, it will bounce around the copper walls of your detector and eventually can make it into the detector. That process will happen with some probability. Let's call it F, okay? Now, if we knew that probability, we would be able to calculate the n electron rate, with n going from 1 to 6. The idea here is that, for instance, if a track passes and creates, say, 10 photons, each one of them can make it into the detector with a probability F. And if you knew F, you will be able to calculate how many photons make it into the detector by just using the binomial probability distribution. So that's simple. The binomial distribution will be just characterized by this unique number F. Okay. So if we knew F, we will be able to calculate the n electron spectrum seen by SuperCDMS HVeV. Now, one way to know F is to actually perform a detector simulation and see how many of these photons eventually get absorbed here. However, we can't do that. So we're not part of the SuperCDMS collaboration, so we don't have all the data from their detector setup, etc. And moreover, it's just a really hard simulation to do that the collaboration needs to do. So instead, what we're going to do to get a back of the envelope estimate on the background is to fit this probability F to data, okay? So if we fit this unique probability F to data, we can predict 6 observables, namely the n electron rate, with n going from 1 to 6. Okay. So let's fit the probability to the data. And the answer that you get is that if as little as 1 Cherenkov photon out of 1,000 makes it into the detector, then you can explain the background seen by SuperCDMS HVeV. The smallness of the required probability is indicative of the gigantic number of Cherenkov photons that are being created and therefore that can make it into your detector. In other words, the way that you should think about the SuperCDMS HVeV experiment background-wise is that tracks pass and create a whole soup of Cherenkov photons which are flying around your detector, bouncing in the copper walls. A tiny number of them can get absorbed in the detector, but those that are, they constitute backgrounds. Okay? So after fitting this probability to data, then we can calculate the n electron spectrum at SuperCDMS HVeV, and this is the answer. So here the dots are the data, and the line is our estimation, okay, using the approximations that I just told you. And this horizontal axis is the n electron beam. So this is the 1 electron beam through the 6 electron beam, okay? So from this figure, you immediately see that the 1 electron beam we cannot explain with our Cherenkov backgrounds, but that's fine because they have an hypothesis for that, the origin of the 1 electron beam. They want to understand the 2 to 6. But the 2 to 6, you see that our explanation matches the spectrum very nicely, very, very nicely. So the fact that our spectrum is matching so well, the one measured by SuperCDMS HVeV, we take as pretty strong evidence in favor of our interpretation of the background events that are being observed by SuperCDMS HVeV. Okay. Okay, so let's move to SnowLab, to things that will happen at SnowLab. And in particular, let's take a look at the SuperCDMS at SnowLab experiment. And let's see how these backgrounds can affect the reach of SuperCDMS at SnowLab. Okay. So the idea here will be the following. So SuperCDMS at SnowLab will have two types of detectors. One called the high voltage, which works in a similar way that SuperCDMS HVeV with an Egana-Ugrinovic effect, which targets low mass dark matter, and the other one is the ICIP detector. Now I'm just going to talk about the high voltage detector. I'm not going to talk about backgrounds for the ICIP, okay? Just backgrounds for the high voltage detector. So the idea on how backgrounds are going to be realized in this experiment is the following. So the high voltage detector, they will be organized in two towers. Each one of the towers will consist of 6 detectors. And each one of these detectors looks as follows. You have a semiconductor target, which will be silicon or germanium, which is surrounded by some metallic housing, copper, and then it will be held by some dielectric clamps, which are made out of cerlex. And around this semiconductor, you also find additional cerlex in some pores. Okay. So the idea on how backgrounds are going to be realized is the following. Cerlex has a known radioactivity rate of a few millibecquerels per kilogram. Now, from the radiative decays of uranium and thorium, etc., you will generate betas, electrons, just with energies of I don't know, like a few hundred keVs. Okay, these electrons that go within the cerlex, which is uninstrumented, will generate low energy photons via the Cherenkov process for sure. And in addition, it may generate low energy photons via radiative recombination. We just don't know because we don't know exactly what are the optical properties of cerlex. But Cherenkov photons, they will be generated for sure. Now, given the amount of mass of cerlex within their detector, which is known from the SuperCDMS at SnowLab proposals, we can estimate the number of tracks that will pass through the cerlex from these radioactive decays. And from that, we can estimate the number of events that will constitute backgrounds by creating Cherenkov photons that will make it into the high voltage detector. Okay. And that can be easily done. And the answer is that you will get roughly 130 events per day per tower. So in other words, 130 tracks that pass through the cerlex create Cherenkov photons that make it into your high voltage detector and constitute backgrounds. Now, if you sum up the energy of all these Cherenkov photons, that energy per event will be likely below 100 electron volts. That means that this background will only contaminate the low energy beams of the high voltage surges. Okay. However, we can compare the backgrounds that these Cherenkov photons constitute with respect to the backgrounds that SuperCDMS at SnowLab was expecting at low energies. So let's concentrate on energies below 100 electron volts, so energy depositions below 100 electron volts. So most of these 130 events per day per tower are below 100 electron volts. And the estimation by SuperCDMS SnowLab with the backgrounds that were known at the moment of publication of their proposal paper is that the backgrounds were going to be at the order of 0.1 per day per tower. So these new backgrounds that we're talking about are 3 orders of magnitude larger. Okay, so these processes are clearly a source of concern. Now, of course, there are many cuts that will get rid of many of these backgrounds here, but that's something that needs to be studied in order to understand the true impact of these background processes at SnowLab. Okay, great. So these backgrounds are a problem. What do we do to mitigate them? Well, first of all, before moving on, I just want to say that we have studied these backgrounds in already 3 experiments, but you see that these backgrounds are rather universal. Most light dark matter experiments look similar. It's a semiconductor target with some copper housing, tracks will pass, will create photons. So these backgrounds do affect several light dark matter detectors. So what can we do? Well, the first strategy is, of course, it's obvious. Just increase any active or passive shielding. In particular, active shielding is very efficient. In other words, if you make shieldings which scintillate, for instance, in the presence of tracks, then you can veto those tracks using the scintillation light that they create. So that strategy is actually already used by some experiments, in particular it's used by CREST, and it's very efficient at mitigating backgrounds coming from tracks. Another possibility is to minimize the amount of dielectric materials which are within your detector metallic housing. For instance, the background that SuperCDMS HVeV is seeing is because they have two large pieces of plastic, which are the plastic circuit boards on top and on the bottom of the silicon target, which are uninstrumented. And tracks pass through those things and create Cherenkov photons and lead to a large number of backgrounds. So any detector strategy, any detector concept that you want to implement, you better get rid of as much dielectric materials as possible. The Serlex clamps in the SuperCDMS Snow Lab experiment are also a source of backgrounds, for instance. Perhaps that they can be changed by metals, and then it needs to be studied if a metallic clamp will get rid of backgrounds or will introduce other problems. That needs to be studied. Another possibility, which is actually being nicely implemented at SuperCDMS Snow Lab, is to use multiple detectors. Okay, so the idea here is that if a track passes, say through some uninstrumented materials, such as the plastic circuit boards of SuperCDMS HVeV, if you have two detectors, then this track will lead to many Cherenkovs. Some of them will get absorbed in one, and some of them will get absorbed in the other. While a dark matter event will scatter only out of one of these detectors. Therefore, by using coincidences, you will be able to veto these backgrounds coming from tracks. That's another possibility. And it's actually being implemented at some future experiments. Another possibility, which is totally not trivial and was never explored before to the best of our knowledge, it's a mitigation strategy that can be implemented in CCD-based light dark matter detectors, such as SENSEI. Okay. The idea here is the following. The idea here is that a large chunk of the backgrounds at SENSEI and CCD-based experiments that reach low energy thresholds will be tracks that pass through the backside of the CCD, where you have this highly doped layer. So this layer of phosphorus doped silicon, okay, which is very scintillating. So any track that passes through it will generate low energy photons via radiative recombination that will constitute backgrounds. Now there's a process that's called thinning that gets rid of part of the backside of the CCD, which is used in astronomy, but was not believed to be important in light dark matter detectors. If you thin the backside of the CCD, perhaps you can get rid of this phosphorus top layer, and in that way minimize backgrounds coming from radiative recombination. So that's a possibility that definitely needs to be studied. Another possibility is that could mitigate backgrounds is that many of these low energy photons make it into your detector after bouncing in the copper walls of your housing. So one possibility is that you coat these copper walls, for instance, with some black paint or something, so that any photon that makes it into the wall gets absorbed there and doesn't make it eventually into the detector by bouncing. Okay, so that will definitely minimize backgrounds in experiments like SuperCDMS HVeV, where these bounces can be important. Now, of course, you need to make sure that whatever paint you put here doesn't lead to backgrounds itself, and that needs to be studied. Okay. And finally, this is not a mitigation strategy, but it's just a subtraction strategy. If you knew very exactly the material properties of your detector, any tiny piece of material in your detector, you will be able to simulate backgrounds and perform background subtraction. But for that, you really need to know your detector well. For instance, in SENSEI, there's some glue that glues the pitch adapter with the CCD. And this glue may absorb photons, and therefore it may, some of the Cherenkov or radiative recombination photons can get absorbed here. However, the properties of this glue are not very well known. They have not been measured. Therefore, there's an intrinsic systematic in any calculation of backgrounds that we do at SENSEI, coming just from the fact there's glue there. At SuperCDMS HVeV, the plastic circuit boards are made out of some composite plastic, and we don't know exactly what it is. We took some reasonable estimate of what it could be, but we don't know what it is. So if you knew exactly what your plastic circuit board made of, you would be able to do a very precise background simulation and then subtract those backgrounds from your data. Finally, I just want to point out that there have been very interesting but bold proposals to, in the future, try to detect light dark matter not via the creation of electron hole pairs, but via the creation of single phonon events. So the idea here is that you will have a detector that dark matter comes and create a single phonon, okay, that then will get detected using a TES or something like that. And the backgrounds for those kind of proposals, which are admittedly quite futuristic, are unknown. Okay, they have not been studied in detail. And I just want to point out that the processes that we're discussing now, radiative recombination and or the recombination of electron hole pairs and Cherenkov photons, they can constitute backgrounds in this type of futuristic detectors. And the idea here is the following. So if a track passes through any auxiliary materials that hold your detector, like any plastic holder that is holding your detector, and that plastic holder is not instrumented, it will create, for instance, a bunch of electron hole pairs. Those electron hole pairs can recombine now not radiatively, but non-radiatively via the emission of phonons, not photons. Those phonons there can travel around and then eventually make it into your detector and constitute a background. Another possibility is that this track can create low energy Cherenkov photons, which then can travel through your detector though, and these detectors are usually polar materials, so these photons can be converted into phonons, and in this way they also constitute backgrounds. Okay, so those ideas also need to be explored. So to conclude, we discussed two important backgrounds that affect a variety of light-dark matter experiments, Cherenkov radiation and radiative recombination. We showed that they are a likely, very likely explanation for the excess events seen by both SENSEI and the SuperCDMS HVeV collaborations, even though we cannot ensure that these are the only or the leading source of backgrounds on SENSEI and SuperCDMS HVeV at this point. We are improving our SENSEI simulation to see what's the extent of these backgrounds in detail. But all the evidence points in favor of these backgrounds being the ones that we are discussing now, Cherenkov radiative recombination. And finally, we also discussed very concrete mitigation strategies that can be taken in order to significantly suppress its backgrounds in the future and improve the reach of future detectors to discover dark matter. Thank you.
Thank you very much, Daniel, for the very nice talk. Are there any questions? If you have a question, Chris, I see you unmute yourself, so maybe you have a question.
I do. I hope I'm clear. Am I audible?
Yes, very nice.
Good. So that was a terrific talk, and I'm going to ask you a question about a side point you made about a third of the way through, in which you said you were able to do diffusion calculations of the electrons in the material to estimate the relative yields of the different photons. Just wondering if those diffusion calculations were specific to semiconductors or if they could be applied to other ionization detectors like liquid argon.
Yeah, so the calculations that we're doing, the simulations that we're doing are specific to semiconductors. And the reason is that in order for you to do those calculations, you need to know exactly what are your materials, and those calculations are extremely material dependent. So in semiconductors, there are very specific processes by which electron holes can recombine. Those processes are radiative recombination, trap-assisted recombination, where you have an impurity level within the valence band and the conduction band over which electrons and holes can first go emitting phonons, Auger recombination. Okay, those are the main processes. Therefore, our simulation includes those processes, and it includes the diffusion of electron hole pairs within the specific semiconductor that we have, which is silicon, because there are specific diffusion constants also that go for silicon. So I'm not entirely sure how generalizable is this to liquid detectors. Definitely, they are generalizable to other semiconductors. Liquids, I'm less familiar on what are the possibilities.
Thanks very much.
Are there any other question, comment for Daniel? I have one then. So how this interpretation will fit CREST result and the access that they are seeing with the fact that they are using the eye stick for getting the events that are crossing?
Yeah, CREST is a terrific experiment. Or backgrounds do not affect them. And the reason is that they have just they have excellent active shielding. So we discussed with CREST if these tracks can constitute backgrounds. We kind of concluded that they can't, because in any track that passes, they will not.
Yeah, but they are still seeing a rise at low energy.
I know,
right?
We don't know.
And how this is, okay.
Yeah, we cannot interpret it within our processes that we're discussing here.
Okay.
And we discussed with them, and they don't really know yet, to the best of my knowledge, what is that rise. But it's not the processes that we're discussing here.
Okay.
Yeah, we can explain some excesses, but not all of them.
And follow up, since you have done the study for HVeV run 1, does the result reflect the run 2, the HVeV run 2 with the longer exposure, including the charge trapping and the impact ionization?
So our estimation is for the 2019 data with effective exposure of 1 gram day.
Yeah.
We haven't done it for other exposures. Now, what I can tell you is that I have heard that the SuperCDMS HVeV, some of the members of the SuperCDMS HVeV collaboration are already saying in words, in talks, that they believe that the backgrounds that we're discussing are indeed their leading backgrounds for the 2 to 6 electron beam. But they have not made a formal statement about that.
Yes, yes. Okay, thank you. Are there any other questions for Daniel? Maurice.
Yes, may I ask a question? Sorry, I reached your your talk a little late. I had some bad meeting this day. Are you trying to explain what Kurinsky explained as maybe dark matter?
Partially, yes.
Okay, so, and in his paper, he have a lot to say on the Edelweiss experiment. So have you some explanation which can suit Edelweiss background in terms of nothing and certainly not dark matter?
Yeah, so their paper heavily relies on the X seen by Edelweiss. Now, they also try to make the argument that this is more general and all the experiments are seeing these X's, and they also talk a bit about SENSEI, etc. So my answer was partially yes, because definitely our backgrounds are explaining SENSEI and SuperCDMS HVeV, but they cannot explain Edelweiss. And the reason is that Edelweiss is very, very deep underground, and it was very well shielded. So the rate for tracks at Edelweiss was very small. So we did try to estimate how many backgrounds could we get from Edelweiss using these 2 processes, Cherenkov radiation and radiative recombination. And the way that we did that is the following. So Edelweiss has, again, excellent timing resolution. So any backgrounds that could arise from tracks will arise from non-instrumented materials around the Edelweiss detector. In particular, Edelweiss has some Teflon around it and some sapphire balls which hold the detector. And the radioactivity, and under some assumptions, some reasonable assumptions for the reactivity rate of those dielectric materials, we calculated the amount of tracks that will pass through those dielectric materials, create low energy photons, and make it into the detector. And the answer that we got is that the number of events that we get out of these processes is tiny in comparison with the rate of events that they are observing. So we cannot explain the rate of events seen by Edelweiss. So my answer was partially yes, because we explain some of the experiments, but we don't explain all of them.
Well, I have to say that when Kurinsky published his paper, well, we didn't believe immediately that was dark matter. And of course, background is very, very difficult to track, especially when it is low. So, well, your explanation in other experiments are interesting. We probably should think a little more on everything, and of course, before thinking that it may be dark matter.
Absolutely,
long path.
Yeah, in that we agree.
Okay, well, thank you for your explanation, and I have to say that I'm dubious about dark matter. I mean Edelweiss, even though I'm participating from the beginning, but well.
I deeply share your feeling.
Okay.
Thanks, Maurice. I see Jeter with his hand up. So, Jeter.
Yes, thank you for the nice talk. I think these photon backgrounds are certainly going to be more and more important down at these low energies. I guess I had 2 quick questions. Hopefully they're quick. What is the time scale that you think? I'm just wondering if something like SENSEI, these CCD-based searches, if they change their technology a bit and got better timing, if you think that that would remove a lot of these events. And then on the other side, I'm wondering if you're thinking about other sources of low energy photons for some of these searches that want to go below an EV. It seems like Cherenkov radiation drops off pretty quickly as you go to low energies. So I'm wondering if there are other sources that might become important down there.
Yeah, those are great questions. So so let me start with the source of. Let me start with the first question. That is just SENSEI. How are they going to mitigate this thing in timing? So SENSEI won't have better timing, to the best of my knowledge. So SENSEI is now in the process of being deployed. My understanding is I'm not part of the SENSEI collaboration, but it's in the process of being deployed at some level, and they won't have timing resolution to get rid of these events. What they will have, though, is a much lower track rate, which is much lower than what they had at Minos. Therefore, the backgrounds, these low energy photons will get down just from the fact that there will be less tracks passing through their detector. Okay, so and the improvement should be significant because they expect their design, by design, they expect that they will have a track rate which is, I believe, 2 to 3 orders of magnitude less than what they had in Minos. So these backgrounds will get significantly better. Now, that doesn't mean that they do not need to explore mitigation strategies. In particular, they are exploring, my understanding is that they are exploring the possibility of thinning the backside of the CCD, because it may be that the radiative recombination photons dominate their backgrounds actually, and if they thin the backside of the CCD, it may be that they get rid of those backgrounds. And actually that will, to a large degree, depend on what we get out of our more precise simulations. So if once we do the simulation of the backside very precisely, we'll be able to tell them a number, and we'll be able to tell them, okay, look, if you thin this thing, then you will get less events by this number, etc. So to some degree, they are waiting to what we get. And regarding lower energy events, which is your second question, so it turns out that the Cherenkov rate is kind of flat down to, in materials such as silicon and germanium, which are non-polar, the Cherenkov rate, the Cherenkov emission rate, the differential rate is constant down to 0 electron volts. So you can get Cherenkov photons from, say, 1 milli electron volt up to essentially the threshold, which is 4 electron volts, the threshold for Cherenkov radiation, and the rate is pretty flat. Okay, so this, once you go towards lower energies, and that's why these backgrounds can be important, for instance, for the single photon detectors, you can get, say, 10 milli electron volt Cherenkovs that they will contaminate your signal region. So that's definitely a source of concern. Now, for non-polar materials, the situation is much more complicated, and the reason is that for polar materials react very strongly to light, so the dielectric function at low energies has very strong peaks in the polar resonant regions, and there the Cherenkov rates just blow up. But also the material becomes very absorptive. So then it's unclear what will happen in those kind of materials, which also have been proposed for single photon detection. But silicon and germanium, short answer is that Cherenkov goes down to 0 electron volts, like whatever, as low as you want.
Thank
you. Gilles, you're next.
Yes, hello. Thank you. Very good talk. So my summary would be that for deep underground experiments, so this rate is going to drop a lot, right?
Yes.
And and also second point is that you need some kind of dielectric material to explain, to account for this Cherenkov process, right?
Yes.
So I am part of a NewsG experiment, which is trying to get also very low mass WIMPs, I would say, and not so much electronic recoils, but at least nuclear recoils. And we do observe a lot of huge, so this is gaseous detector. So we can get to single electron ionization, which is, okay, more in the 13 or 30 eV. It's not 3 eV, but still we observe a lot of single electrons as well. Now we have a gas. So I'm wondering, okay, probably we have to investigate how much this could be a source. But on the other hand, we do not have inside the detector dielectric. So I'm not sure.
Do you have something dielectric around it, like anything that is non-conducting around it that holds your detector? Anything?
Well, but it's you know, we have a shell. It's a spherical gas detector. The shell is metallic, so there is some dielectric outside, of course, but there is a few centimeters of copper between external dielectric inside. So we have a few grams inside of dielectric, maybe from. Okay. Anyway, so interesting. We will try to see if, or maybe we can work together to see if it makes sense to see if it's a source or not.
Yeah, absolutely. If you have if you want to discuss it, be happy to.
Okay. Thank you.
Yeah. Now, just give one comment regarding the fact that you go deep underground and the thing will improve. That's true, but it will only improve once, in the sense that you go deep underground and you improve the background, but then if you scale up in volume, you won't gain any sensitivity because this background also scales up with volume in detectors such as SENSEI. So your signal will scale up as volume, but your background will scale up equally as well with volume. So signal over background will stay constant. So you won't gain any more reach.
Okay, I have to think about it.
So it's a tricky thing. If you will improve once by 2 orders of magnitude by taking a 2 orders of magnitude less track rate, but after you reach that, you need to impose mitigation strategies.
Okay, thanks.
Are there other questions?
Sorry.
Go ahead, Maurice.
What I have heard, because we are very puzzled by Kurinsky paper, and the main thing he has said on our experiment was that the background was roughly the same at surface experiment and down.
Exactly.
So I cannot catch how you would explain that, and we do not make any explain. And I'm not saying that it's dark matter, but it is very complicated to understand why, at the lowest energy spectrum, it's the same on surface and at 1.7 kilometer underground lab.
Absolutely. So my answer to that, and then Noah's paper relies heavily on that fact. And my answer to that is that that's only a factoid. So I'm trying to show here that in some experiments, the events are just due to tracks. Therefore, that universality of backgrounds cannot be true. So that statement there is just, it turned out to be a coincidence. But here I'm showing you with numbers that these particular type of backgrounds, which do exist and do seem to be a significant concern for both SENSEI and SuperCDMS, are correlated with the number of tracks. That means that there must be another explanation for experiments that are deep underground and they do not have large number of tracks.
Okay, by the way, I will ask my group to invite you to give such a conference, because it's interesting. Well, you are at least trying to say to people, be careful with everything you have in your experiment if really you want to do that. Will it be possible to maybe have an exchange like that with Zoom?
Yeah, absolutely. So
okay,
no
I can start an email if so. You can you have
okay.
your email address and you can
fine
the discussion.
Yeah, let me just stress that we cannot really explain it otherwise. So
but well,
yeah.
It's interesting to hear some people who explain why the other may have that, and then other people will think a little more on everything in the experiment, and that's needed, of course.
I agree. I mean, we are exploring a new kinematical regime of the standard model. So it's unsurprising that there's new stuff down there.
So I don't see any other hands up. So if that was the last comment and question, I would like to thank Danielle again. Thank you very much. And you're always welcome to come to Snow Lab for a visit when it will be possible.
And the situation is
and I will send the email to